accidents. So I'm modeling like Fukushima transient with EDF code which is called MAP. I will talk a little bit about that later on. So yeah, my job is to do code improvement, to make the code more realistic in order to be more validated against experiment, to make sure the evaluation you make are okay for safety analysis and for the regulator, as I was mentioned by Sean just earlier. Yeah, good. So before I'll start, I'll give you the outline of the presentation. I will give you a very, very short introduction to the nuclear safety, very short, so a few slides. Then I will talk about transient and severe accident modeling. So I will go to the physical phenomena to consider when we're talking about the transient. What do I have to model? Then I will talk about modeling the ESMR. So this is a design of SMR we have taken into account in the ELSMOR project. So how do we model that with the EDF map code? Yeah. So, and then I will talk about TBC scenarios to be modeled. So there is different package in the ELSMOR project. There is a 5.2 with a more like DBC accident, which means like there is no severe accident, no co-degradation. And the 5.3 is like we have co-degradation. We are going to look at it more precisely. So we'll talk also about this severe accident scenario to be modeled. And also I will give you some preliminary results of two transient, station blackout, and a local transient. So I will detail a little bit later what it means. Maybe not everybody is aware, but I will talk about that. And then give you some elements for conclusion. So before I go to the, let's say, the real accidents, just a short introduction to nuclear safety. So do you know what is a risk? And is it equivalent to a danger? Is somebody knows here? Like let's say, is it dangerous to do some skydiving? Or is it risky? Is it dangerous to fly a plane, or is it risky? Do you have elements? It is risky. You say it's risky? Did you say it's risky?
In terms of mathematical or like a nuclear approach to risk, it's like how dangerous it can be, and also considering how frequent it happens. So it might be a lot dangerous.
Yeah, correct.
If it doesn't happen very often, then the risk is low.
Exactly. It's exactly. So of course, if you take a plane, for example, if you fly, it's dangerous because you can have a crash, right? So it's dangerous. But is it risky? It's not risky because a crash, it's not so often. We hear about some plane crash or some skydiving issues, right? So yeah. So what is a risk? A risk is an exposition to a danger or damaging event during situation or activity. It's defined by the probability of this dangerous or damaging situation. So there is just a kind of a very small equation. So risk is a probability times the consequences. Exactly what you mean, depending on the frequency of the situation, right? So this approach, we use that for the safety of nuclear reactors. So this is what is considered. So if you have, let's say, a danger here, which means, let's say, a station blackout, like a break in a plant, it's dangerous, right? Because you can have, if you don't have, let's say, safety systems, you can have a co-degradation and a release of fission product in the environment, right? So this is dangerous, but we have to evaluate the risk. So here, sorry, there are some French words, but you will understand easily. It's probability and consequences. So a given danger is hence associated to a risk through a probability and the impact of its consequences. So now we know that. Let's look at the Farmer diagram. Maybe you have already seen that before. Yeah, the Farmer diagram is very known. So here you have, let's say, the frequency or the probability of, let's say, an accident or an event. And here you have the severity or consequences. And this is a line. So we say here below this line, it's acceptable. Above this line, it's not acceptable. You see that what I mean? So let's say I have a very frequent situation happening every day. I have to have very, very low consequences. It has to be very, like, modest. I don't know the word, but it has to be very low as consequences. But there is, there is still some. Sorry. If you have a very small frequency, say it has happened every 25 years or something, like a severe accident, Fukushima or TMI or something like this. So I have to have. I can accept to have a higher severity. It's the way we're working through the, let's say, in the nuclear safety. So this way, if you go this way, is prevention. We try to reduce the apparition of this accident, and this is a mitigation. Sorry. So we want to reduce the consequences. So it's easy to understand. And also, there is something we call the residual risk. Do you know what it can be? Residual here. There is this residual risk. It means that whatever we do, we cannot. Sorry, I cannot get rid of it. Right? It will. You can do everything. It can still happen. Can you give me an example? I don't know. No?
The earthquake?
The earthquake. It can be earthquake. But earthquake, we know the frequency, right? Yeah. Maybe residual risk is like a meteorite. You know, meteorite will come and crash to the reactor. It's possible, right?
Yeah.
We cannot eliminate it. You know, so we have to consider it, and it may have, let's say, severe consequences. But you know, we have to take that into account too, right? So now let's talk about the transient we look at. Here is the frequency. Let's say the frequency by year for the kind of reactor. Here you have the normal operating condition. Let's say, like we have a hot shutdown, which means the reactor is stop. You know, it's in a safe position, and there is nothing happening, right? It's just in a hot position, and it happens, let's say, many times a year, right? Normal operating condition is what we call category 1. It's it happens all the time. Then you have the incidence. So the frequency is between 1 and 10 to the minus 2, right? So for example, you have transient like a station blackout or a loss of feed water. You know, those transient, like station blackout is like the Fukushima initiator. So station blackout. Loss of feed water is like your steam generator are not, alimented by, there is no water anymore inside for cooling the steam generators. If you go to accident now, accident is like more severe. You have more consequences, but the probability is lower. So this is category 3. It can be a small break loca. Loca is a loss of coolant accident, which means you have a break inside in a pipe, or in an SMR you can have a break. Then you will have water flowing. The level of water will decrease if you do nothing. Sorry. One time you may have, if you don't have any kind of safety system, it may lead to a severe accident. So yeah, if we have safety system, we can manage the accident, and we won't have any kind of co-degradation. And the probability of those kind of transient, like steam line break also, and steam generator tube rupture. Steam generator tube rupture is a rupture between the primary circuit, and the secondary circuit. So you have in the primary circuit you have some reactivity, right? Radioactivity, and in the secondary circuit you don't have much. Yeah. So if you have a break, you will be able to transfer radioactivity directly from the primary side directly to the environment, because the secondary side is directly linked to the environment. So yeah, so we have to consider those transient. And then what we call like hypothetical accident is like large break loca, a big break, or a main feed water break, which means that the pipe feeding the steam generator is broken, completely broken. So we won't be able to inject any more into the steam generator. So the category is number 4. So those transients are called DBA or DBC accident, designed by this accident, designed by this condition. And you can see, you can look at the probability. Then, as it was mentioned this morning by Eric from CA, you have deck A and deck B, which means that are transient less probable. The frequency is much lower, but the consequences are higher. So we can have a co-degradation here. And it's what I'm going to show you in, let's say, a few minutes. So now we know a little bit more about the safety and how it works. Let's look at the physics now. Let's say more interesting part. So in order to model an accident potentially leading to a severe accident, in an SMR or let's say a PWR, like a classical reactor, many physical phenomena must be modeled in both the reactor coolant system, the primary side, let's say, and the secondary side, and also to the containment. We have to evaluate the releases and so on. So here is an example. This is just an example of, it's for a PWR, right? But for a small modular reactor, it will apply also. So let's say, in a PWR, we have to model, the natural circulations. Let's say you have lost your pump, the pump are off. So if the pump trips, it happens a lot. In a year, the frequency is very high. So we have to to be able to evaluate the natural circulation inside the reactor coolant system. We have to be able, for example, to evaluate what is the heat transfer from the core, the basics of the physics. We have to be able to see what is going on the pressurizers, the heaters, the sprays, the heat exchange in the steam generator, many things. I'm not going to detail everything, but we have to take into account many different systems. Let's say if you have safety injection, emergency safety functions have to be taken into account too, right? So, and then if you go to a severe accident, things are much more complicated than that if you are looking at a DBA accident. So then, if you look at severe accident, you have to look at the zirconium. The zirconium is cladding. It will oxidize with water, steam, and then you will create a lot of hydrogen, huge mass of hydrogen. This hydrogen is very, the reaction is very exothermical, and it produces a lot of heat. And this heat has to be added to the decay heat. So it's like twice the decay heat we have to evacuate. So we have to calculate all that. And if we do nothing, let's say we have co-degradation, then there will be like corium, which is kind of magma between the uranium, zirconium, steel in the core. Everything will melt, and then we have this kind of magma relocating to the lower head. It's what we see here. So we have to evaluate the flux. So I will show you a video about that. We have to evaluate the flux between the corium and the vessel to see if there can be a breach in the vessel and what condition, what we can expect. So this is for the only for the reactor coolant system and secondary side. Let's say this is for the containment. So many other different physical phenomena to model. So for example, you can have I don't know, you can have a quench tank flashing, if you have a transient with the cooling of the primary circuit, then the pressure will increase, then you will, there will be a flow between the pressurizer and this quench tank in order to keep the water, but when there is too much water, it will flow, there will be a break, and then it will flow directly to the containment. You have to look at the aerosol deposition if you have fission product releases. You have to look at the condensation. You have to look at the spray if you have spray. Maybe you can have fan coolers, or you have to look at the hydrogen chemistry. So it's a lot of different physics to look at. So yeah, I just tried to write here what we have as a slide before. So the physical phenomena to consider. So it's not an exhaustive list, of course. So you have to consider the thermohydraulics in the RCS and secondary circuits, in the containment tool, the core degradation and melting, if we have, the zirconium oxidation at high temperature, the potential exergetic H2 burns. I didn't talk about that, but hydrogen is it's a gas, and it can burn and leads to like a big combustion, like in Fukushima, for example. That could be devastating for the containment. So we want to get rid of that. We want to be able to stop that before it happens. So we do some things in the reactor like recombiners, or we can use like igniters too. So we have to look at the fission product releases also in the core, from the core and to the containment and the environment. The possibility of a reactor breaching at a high pressure, which is like when there is, when the corium is there, and then it's attacking. It's like creep rupture. It can be a creep rupture, and it will have big consequences in the containment and maybe into the environment. So also there is a thermochemistry and the thermal exchanges in the lower head. For the what I call the IVMR, I will talk a little bit later. IVMR is a strategy we use in the ESMR design. So we want the corium, the corium, the magma, we want to stay inside the vessel. We don't want any breach. So we are trying to cool it down with water outside in order to make sure there is no breach. And this is all the radioactivity will stay, or a big part of the radioactivity will stay inside the vessel. So it's, let's say, safer, right? So look at the iodine chemistry, aerosol deposition, and so on. So each physical model has to be validated, right? You cannot use it just because you have made a new equation. You have to validate it against experiment or code-to-code comparison. Sorry. On an already validated code. This code is good. We're going to compare. Also, to ensure this is valid, right? Some models may interact with others. It's very complicated. It's not only small things. And in order to make sure all those couplings are well taken into account, so we have, let's say, different levels of validations. So we have what we call the separate effect, so which means we are looking at separate physics, let's say thermoanalytics or fission products analysis or just chorium, heat flux, So we have experiments here like BETSIS for thermoanalytics, live for the chorium behavior. Also we have what we call integral benchmarking. Integral benchmarking is like we have like a small reactor, small scale, and for example we have the Phoebus experiment. Phoebus experiment is a CA experiment, IRSN. It was in the 90s. It was a French experiment. They used like real assemblies, and they had a severe accident there to look at how the fission products, how the cladding will heat, how it will melt, how the fission product will, distribute inside this reactor. And then after that, we have, of course, the real reactor cases, like the TMI. TMI is a big one for the severe accident analysis, and later the Fukushima accident. So we use that to improve our codes and to be able to model those accidents. So as I said, a lot of R&D is necessary to do this kind of activity, and to ensure that the code can model a transient like a transient or a transient leading to a severe accident, both. And of course, not all the physics are perfectly known at this time, especially for severe accident. Many research are going on. So if you like to work in this field, it's very, very interesting. You have a lot to learn. It's not everything is not written down. You can do by yourself, things. Now I will talk about the modeling. How do we model the ESMR with map code? So map, there are many different codes, right? I will show you map, but all the codes they use, let's say they have similarities, of course. So map, which stands for Modular Accident Analysis Program. It's an EPRI code, which is the Electric Power Research Institute. It's in the US. So it enables to model both transient in severe accident for PWRs, and SMRs. Also, it can model like BWRs, the reactor like Fukushima, like boiling water reactors. And for example, it can also model the VDER, let's say the Russian type reactors, and also the CANDU, like with our Canadian colleague, you have a version to model the CANDU too. So yes, this code is used internationally. We use it in France, it's used in Japan, in England, in all the utilities in the US, in Canada, it's used. So it's used in North Korea. A lot of people are using it to model their severe accident, especially severe accident, and do what we call the PRA, probabilistic reliability assessment. Yeah, you know that. So yeah, so this is, for example, the meshing we have used for the ESMR, design. It's very simple, right? You have only a few number of mesh, right? It's not a detailed code like WLAP or I don't know Kata. So you have, let's say, 10 nodes, but it allows to model all the vessel. So you have the lower head here, you have the core, the plenum, let's say the hot leg cone, the hot leg riser, and then the water is pumped from here. It's getting hot here through the core, and then it's cooling down through the steam generator here, and then getting back to the downcomer and back to the core, right? It's a very easy modelization, but it gives good. So it's what I tell here. It's let's say coarse modeling for thermohydraulics, right? But it gives good result compared to, let's say, internationally known code like Kata, or let's say WLAP, maybe. So Kata is a French code for thermohydraulics. It's developed by CEA, and it's used a lot in France for safety analysis and transient analysis. So we did some comparison, and we have with map we have some good agreement. Also, the thing I have to say is that the EPRI code was not directly able to model this kind of reactor, right? Because of the steam generator are specific. Our colleague Eric, earlier this morning, he talked about plate condenser. It's not like tube condenser, safety generator, sorry. Safety generator. So yeah, so we had to adapt some modeling, to be able to address that, to take into account those kind of transients. But once we have done that, it works well, right? So map enables to model the transient physics in both, as I said before, the RCS and the containment. This is let's say, like a strength of this code. You can do all at once. And in particular, the phenomena occurring in the containment of the ESMR is extremely important, such as the condensation. When you have a severe accident, or even an accident, classical DBA accident, you will have like steam getting outside of the vessel here through a break, for example, and then this steam will go up, and then since there is a water wall, you can see here, it will condensate through the wall and get back to the, let's say, what we call here the sparkle pool. So it will have a big impact on the pressure, you know, and on the correlation you use for the heat transfer here. So it's you know, everything is linked. So yeah, and also there is the hydrogen generation. When you have hydrogen generation, the hydrogen is very, let's say, light compared to air. So it will go up and then go to the containment, and you will not be able to condense that, right? So the concentration should be high, and it could lead to a combustion. So we want to, you know, get rid of that. You know? So also one thing to mention regarding the ESMR compared to let's say a large PWR is that the ESMR, it has a relatively small free volume. You see, like a PWR. Do you know what is the volume of a PWR? Let's say EPR, the big one. What is the free volume in the containment? It's huge. You don't know? It's like 80,000 meters cube. You know, 80,000. It's enormous. You know, you see what I mean? So for this kind of reactor here, what do you know? What could be the volume? No?
5 to 10,000.
Yes. It's like 2,000. You see what I mean? So the power is not so small compared to the EPR power. You know, EPR power is like 4,500 megawatt thermic, right? And this one is like 540. So you know the ratio is not good for him because you have a smaller volume for the, let's say, a higher power. So the density of power is higher. So you have to evacuate the decay heat, right? If you have a severe accident. So we look at it too in the ELSMOR project. So yeah. Now I will try to just to introduce you what kind of scenario we have chosen to model in the WP52 regarding the DBL accident. What kind of transient and what it implies, you know, for the safety analysis. So we have decided to model two different transients in this, let's say, DBA transient analysis. Which the first one is a station blackout. So in a station blackout, I will talk about it later, but you lose everything. You know, you have no more electricity supply, so you have to live by yourself, right? You have to, pumps will stop, and then you have natural circulation, and you will see what is going on. And another transient initiator is a LOCA, a loss of coolant accident. So there is a break inside of the, here, for example. So here you have the vessel, for example, just here, just in the primary side, but at the top of the steam generator, you see that? You will have a break. So the reactor will, you know, depressurize, and then the water will be, if you do nothing, you will be like losing water, right? And the core may heat. There might be a heating, and then the core can degrade at this time. So for the, of course, for the DBA analysis, we assume that we have a safety condenser. So Eric already talked about this this morning. What is a safety condenser? So here you have, for example, the newer design. Here you have the vessel. I don't know if you can see well. And here you have, let's say, inside the vessel, you have the steam generator, the compact steam generators. And then you have this condenser here, right? You have this condenser with valves you can open or not. And there will be natural circulation. It's all passive. You know, so the water is heated by the core. It's going through the steam generator, so it's cooled down. Because there is cold water here, this cold water is heated inside the steam generator and going up because of density purposes. And then it's condensed through the water wall, which is a very big mass of water. The water wall is like 5,000 cubic meter, you know, volume. It's a huge mass of water at a low temperature, let's say 20 to 30 degrees. You know? So it has a big inertia. So it will be able to cool down the reactor, right? So in those transients, since we have one safety condenser out of two, you know, usually you have two. So we assume that there will be no kind of severe accident, and at least for some days because of the inertia of the thermal wall, right? And yeah, So for this calculation, we're going to compare between partners. So some guys will use Qatar, some guys will use Relab, we're going to use MAP. We're going to compare our result and modeling for the same transit. So now let's go a little bit deeper inside the station blackout transient. So station blackout, as I said, you have the loss of the main cooling system. So this will lead to a scrum, reactor scrum. So the reactor rod will get inserted. So you have now, after a few minutes, you will be in decay heat mode. And then you will use the safety condenser, so we call this RFP, to cool down the primary circuit, and of course, evacuate the decay heat, and depressurize the primary circuit. So physics to address, natural convection, primary side, secondary side, and of course, tertiary side. So it's like challenging physically. For the LOCA transient, so the LOCA is a loss of coolant accident. So we have initial break opening here. So we have the loss of the main cooling system. The reactor scrum is reached at a high pressure in the containment. Do you understand why? Can you say why?
Can you repeat the question?
Sorry.
To ensure that the controls are fully inserted?
Yeah, but do you know why? Maybe I did ask why the question, not good the question. The question is, the pressure is going to increase in the containment. Do you know why? Because we have a break.
Because
Not
of the creation
cooling
of the
anymore.
steam.
Yeah, creation. Is that you mean creation of the steam?
Not cooling.
Yeah. In fact, when you open a break, let's say the pressure in the vessel is like 150 bars. It's high pressure. Then it's hot water, right? It's 300 degrees C. So when you open the break, this water will go what we call flash. It will be instantly steam in the containment. So we add a lot of energy in the containment, and this will increase of course the pressure, right? You know this PV, gal, LRT. You know this equation, of course. And then so what many protection exists for the ESMR. One protection is like a stop overpressure. If there is let's say increase in pressure, it's not normal. It's like there is something happening. So we have to stop the reactor because of this high pressure. So, for example, when the pressure reaches like 1.5 bar, 1.5 bar, then you will have the automatic drop of the rods inside the vessel. So yeah. So once you have the the reactor, the rod inserted inside the core, as I mentioned before, you are in a, let's say, decay heat mode. So you have to evacuate the decay heat. But decay heat is not so small, right? It's like, do you know? It's like, do you know what is the range of decay heat? What is the percent of the, let's say, full power? If you have, like this way, you have a local transient or station blackout transient, you insert the rod. After, let's say, 1 second, what is the decay?
7%.
7%, correct. And after, let's say after 7 days, what is the percentage? Do you know that?
0.01.
Yeah, it's very low, right? It's like 0.5%, 0.5%. After, let's say, 50 years, you still have decay heat there, right? But it's very low, right? But so we have to evacuate this decay heat all the time, and this is challenging. So through the condenser, we are going to be able to make it, right? Because the condenser is there. But if there is no condenser, you will see that it will be a different story. I will show you a video now, just after that. So yeah, the physics to address, so I will rapidly through the local analysis, but you understand that you will have a depressurization of the primary circuit. You will have some accumulators. I didn't talk about accumulators, but it's just like passive system, like big tank with a pressurized tank at 45 bars, something. So when the pressure inside the primary vessel is lower than the pressure in the tank, then automatically a valve will open mechanically. And then water will flow inside the core. So it will delay the time we have before, severe accident. It's good for, to save time before we have like something more serious. So the physics to address is the same as usual as before. You have to look at the break flow versus containment pressure, steam condensation on the containment walls, because in this case you have a lot of steam because of the accident. The local, you have a lot of steam, so you have to look at it. And the accumulated discharge too has to be modeled. Yeah. So now let's talk about ELSMOR 5.3, which is like the severe accident analysis by itself. So we are going to model transient 2. a station blackout, same initiator, the consequences are not the same. Station blackout and LOCA. So we assume that there is no safety condenser available and no cooling of the RCS. So we are going to expect core degradation. As the water of the RCS is going to evaporate. And one important thing is the onset timing of the core degradation. The time the core will begin to uncover. It's this time, it will heat very, very fastly. And like 15 minutes, if you have cores that begins to uncover, you can have a severe accident, and you cannot get back. It's like irreversible process. Yeah. So containment pressure and temperature will increase due to the creation of non-condensable gases and hot gases, as I mentioned before. It's a whole thing. So here, for example, you have a picture of a core degradation calculated by map, but I will show you a video now. So just before that, I would just give you the sequence of the transient, so that you understand better. So the station blackout, let's say phase one is the initial phase of the accident. So for the station blackout, you have this loss of main cooling system. So there will be a reactor scrum, automatically, because you have no power, automatically it will drop the rods. And then, I have a question for you. Do you know what will happen then? If we have no cooling, what is going to happen? You have this station blackout, so which means that you have no electricity, no pumps are running, right? No cooling. Then
we have to depressurize
we have to depressurize, right? Because we don't like to have a kind of severe accident with high pressure. But before that, what is going to physically happen?
The reactor will shut down itself, like the SRAM will happen.
There is a scrum, here it's written. But in terms of containment in the coolant system, what is going on?
Passive safety system will be initiated.
There is no passive system there. We assume there is no
The high pressure injection?
high pressure injection. No, we assume there is nothing. It's like Fukushima, nothing is working. It's like, I don't know the word in English, but it's like so it's like there is no driver inside the car. You see? So what is going on? You have no cooling. So the core is still there, the core. So there is decay heat, right? It's going to heat the water, so the pressure is going to increase.
Core meltdown will happen.
Not yet. It's some time before. You're correct, but it's some time before it happens. It's like a few hours. It's not direct like in a minute. So what we call the PORV, the pressurizer relief valve, they are going to open because the pressure is high. It's like 165 bars, something. So it's going to open, close, to evacuate the decay heat. And then the operator realized you're right, the depressurization, because we don't like to have like a high pressure reactor in an accident. So it will depressurize 1 hour after the scrum. We say that 1 hour, the time the guys see what is going on, you look at his procedures. And for this particular transient, we have assumed that some water is injected from the water wall. You see this big water wall? This big pool outside the containment. So we assume that we are injecting a flow 4-5 kilo per second from this pool, and once the pressure in the RCS is lower than 100 bar. But this system is not passive, right? It's an active system, so it has to rely on the battery, and the battery life is like around 12 hours, 10 to 12 hours. So after 12 hours, no more water. So there is no miracle, right? If there is no water, you go to a core degradation. Yeah, I have a video. I don't know if I have to go. Maybe. Just below. It's below. Click here. Below. Below. I think it's below. It should work. Voilà. Okay. Good. Okay. So this is, for example, a map calculation. So for the station blackout transit, so you see the water wall here, the containment here, very small, and you have the vessel here, right? So you can see that. So you can see only the vessel. But it's good to see the severe accident progression. So you see that at the beginning we had a level of water. The level of water is increasing because we are sucking water from this pool, right? After a while it stops, no, because of the battery life. And then we are going to degrade. So I didn't want to show everything at the same time, but it's okay, no worries. We are going to talk a little bit about what's going on. So once all the water is evaporated, you see what I mean? The core is going to melt, producing a lot of hydrogen. Here you have this variable for the hydrogen concentration in the containment. You see that it goes to the 60%. You know 60% is huge. Do you know Shapiro diagram? No? Do you know Shapiro? Shapiro diagram is just that you know if it is possible you have a combustion or not. If you have a concentration of hydrogen higher than 4%, you can have a combustion. Here it's like 60%. So if you do nothing, you will have a combustion. You see? So yeah. And then you will have the core, you know, the core is as melt, and then it's inside the lower head here, and then it's cooled down by the water outside. This water outside is coming from the you know, the water injected in the vessel and then evaporated and produced in the containment. You see? So you have a level of water, and this should be enabled to prevent a vessel breach, let's say, which is very, very damaging for the reactor. So yeah, so I talk of everything, you know, at the same time. It's okay. So after the water injection stops, what I said, no cooling, the water is evaporated, the core recovers, start heat up, hydrogen generated, core melts, and the water outside the vessel, you know, it enables to cool down the whole thing. So we are lucky in that case. The IVR situation is good, especially because we have, let's say, a small core. It's a 540 megawatt. So the decay heat after a while is 2-3 megawatt. You see what I mean? So you don't have any kind of issues because it's a large vessel compared to the decay heat we have to evacuate. So I will show you heat fluxes in a minute. Yeah, this one. So this is a zoom. You know what you see before. You have a zoom of the core here, the support plate here, and you have the vessel lower head here. You know, you have the circular part or ellipsoidal part of the vessel, and then you have the cylindrical part. You know, the straight part of the vessel, and then the bottom. And yes, it is a video too. I'll try to make it work. I don't know. Yeah, it's working. So at the beginning, you see that the level is increasing, you know, the beginning of the transient. And after the while, you will see the core degradation here. And you will see that it go very fast. Whenever you start the core degradation, you cannot stop it easily. Even if you re-inject water, it's not always good. Because you can produce a lot of hydrogen because of the steam reaction. Yeah. Yeah, co-quenching is difficult. Yes. You see the core degradation here, it's hitting here. So here the scale is for hydrogen, but here, of course, when it's red, it's high temperature. It can go up to 2,500 Kelvin, the temperature inside here. And then the vessel, you see that? Maybe it's not very clear, but we calculate the heat fluxes inside the vessel and outside the vessel. If the heat fluxes of the corium is higher than the heat fluxes extracted from the water, you will have like a creep, you know, ablation of the vessel, which could lead to a vessel creep rupture, right? So we want to prevent that. We want to eradicate those things. So we have to ensure that the water is in-house. You know, the circulation of water is good in-house to prevent those breaching. Yeah. So it's just what I wanted to show you for the station blackout. I have the same kind of approach. I don't know if I have still time. I have the same kind of approach for the local transient. So for the local transient, you will have the loss of main cooling system, reactor scram, as we mentioned, and then the operator will still realize the depressurization of the primary circuit, and then the accumulator will start because the pressure is decreasing. So the accumulator mechanically will go inside the vessel and let's say save time. And in the same kind of way as for the station blackout transient, we assume there is injection of clean water, you know, with a limited battery life. This will then go to a severe accident. So yes, maybe the same kind of behavior is to I don't know the word, sorry, is to anticipate. You know, we have to anticipate the same kind of. So initiator is not the same, but for the long time calculation, long time evaluation, you can have the same kind of consequences. Okay, so yeah. So I had the video, but it's very close to the other one. Maybe if we don't have time, I will skip that. I don't know. Yeah, and I'll go directly to the conclusion. So the modeling of accidents and transient with the validated code, it's a key element, to certify the safety of a reactor design, just as was mentioned by our Canadian colleague. Severe accidents are evaluated natively now for SMRs, which was not the case for, let's say, a reactor in France, like the older reactors, 900 megawatts, 3 loops. They were built in the 80s, so they didn't embed, those kind of severe accident analysis at this time. So it's now we are considering, as our Canadian colleagues say, we have every 10 years we have a periodic review, and now severe accidents are modeled, and we have to mitigate the consequences in the French fleet. So it's not because the reactor is old, it's not good. It's like a hot car. If you have a hot car, but let's say every 10 years you modify the engine, you change everything inside. It's like a new car, right? So it's exactly the same for the reactor we have. So the modeling of the ESMR design is challenging because it's less validated than the large-scale PWR. We have less experiment, right? Less code-to-code comparison. So we are going through project, ELSMOR project. There is a new SMR project. The severe accident project is going on. So yeah, it's challenging for us. Simulation results of severe accidents are used for PRA, probabilistic safety analysis. Simulation we have made until now, it shows possible core degradation if we have no safety system for LOCA and station blackout, but there is no what we call LERF, it's large early release frequency. It means that if we have releases, it's possible, but it will be after a while. It will not be just a few hours after the accident. So we have time. And a word to say that some R&D is necessary in the field of accidental transient and severe accident modeling. So you have understood that. And so it's done in different projects. And of course, young people like you are welcome to work with us in that field because it's very challenging. A lot of physics, different physics, different modeling. There is like a code aspect, numerical aspect, physical aspect. It's got a lot of things going on. So thank you. And if you have questions, let me know.
Thanks a lot, Jeremy. I'll open immediately the question and answer from the floor. Please.
May I ask for how many hours the volume is staying the temperature for each the simulation? You said that you never actually how that they have how many hours
if you have a column going to the lower end, you will stay for life. After you have a severe accident. If you have let's say cooling outside the vessel, you have this water outside the vessel, it will cool down the column, right? For a long time. If you have no cooling, maybe it's a good question, if I understand well. If you have no cooling, you say how long can the column stay? It's very fast. It's like 1-2 hours you can have a breach. It's like creep rupture. Creep is like I don't know the word. It's like if you have a whole poster in your house on your wall. If you stay there, it stays there for 10 years. You will see that it will be deformed, right? It's what we call creep. It's a deformation at given strains, or I don't know the word in English. Sorry, at given pressure, right? You have like a gravity pressure. So it's like this. It will do that. So it can be fast. And my colleague, maybe Nikolai, is a kind of specialist in the lower head analysis. So maybe you can discuss with him if you have a specific question.
Thank you. Please.
I just want to know how the lab code is calculated in the equations, because we have a really big modernization. So for FE, for example, from the GRS code, it's like the equations are solved in the middle of a node. So we use more small sizes. And yeah, how is it that looks like there will be how exact is the computation?
Yeah, good. Thank you for the question. As I mentioned, map the modeling the nodes, of the core, and not the core, sorry, the thermodynamics node. Let's say lower head, steam generator casings as a downcomer. It's very large, right? And it uses a lot of correlations. It's not like Qatar. Qatar is 6 equations, or maybe Atlas is like 6 equations, right? So it uses correlation, but it's very efficient. I've made a lot of comparison between Qatar, French code, and this map, and we have, let's say, 10% discrepancy max. So it's very fast. The map is very fast code. It's like, for those calculations I presented here, it's like 5 to 6 hours in a laptop. Some codes like Qatar would take days before you have the calculation done.
The first one question from there, and then please. Please.
So I was just thinking, do you calculate any sort of burn-up effects, like fishing gases, any sort of these things that accumulate in the fuel or in the body materials?
Yeah, burn-up, you can do that. You can put that into the input file.
Okay.
Burn-up, yeah, it's very detailed, in fact.
Yeah, I was thinking, because we're doing some of these simulations with like pure performance codes and so on. I was thinking like sort of transitioning from the standard LDR tool to SMR tool. I was thinking the big question would be how well are the experimental correlations which are fitted to standard water reactor data, how well do they apply the SMR conditions, which are like lower temperature, lower pressure, and so on?
Yeah, you're correct. Yeah, it's a good question too, right?
I guess the question is, have you faced situations in which you're like having difficulty finding experimental correlations or models because the range of operation is different to standard reactors?
For the ESMR, most of the operating conditions are close to the, let's say, large-scale PWR like French reactors. Right, the pressure is the same, temperature is very close. The difference is the height of the core.
Okay.
It's only half of the real, let's say, in a French fleet, it's 4 meters, maybe higher than here. I don't know, maybe let's say this height. And for the SMR, it's only 2 meters, 2.2 meters, something like this. So, but the linear power, the linear power, I don't know, is higher because you have more power compared to the. So the density of power is higher compared to the. But after that, in my field, what I look more precisely is a severe accident or let's say transient analysis. So once there is let's say, rods are inserted, I look at the decay heat and things like this. I do not go to the details of the, as you mentioned, what's going on inside the rod, inside the claddings or the uranium. But some people do that. Yes, thank you for the question.
Please.
I don't know if my question is related or not, but during the modeling, what kind of limitations or challenges that you face code-wise that limits your modeling process? And how would you overcome those?
Yeah, for example, yeah, it's a good question too because usually for example, the containment is challenging to do because it's very small, and usually in a large PWR, the concentration of hydrogen is very low. It's 2-3%. Then because it's very large, even you have high quantity of hydrogen, it will be easy to. So you don't have much non-condensable gases. In this one, you have huge quantity of non-condensable gases. So we have to make sure our correlation, for the condensation on the wall. If you have a lot of non-condensable, it will be different for the steam condensation. So we have to make sure it's working with the concentration we have. It's an example. So for that, for example, we use a benchmark with Qatar. Again, Qatar, French code. So we give our mass and energy release, from the map code, because Qatar is going to stop whenever there is a code degradation. Cannot calculate after that. So we get the mass and energy release as an input in the Qatar, and then they put that in their model, and then try to calculate the pressure, and then compare that to map. And we had good results. So they are using different correlation than ours, but globally the results are coherent. So we know that at least we have some, let's say, globally satisfying result, even if it's not very precise. If we want to go further, we have to do experiments. And for example, one also, it's good to say to you that for example, the water wall is also something difficult to model because we are modeling it very simply. Simplification. We have only one volume, one temperature. Of course, in real life, you will have natural circulation, and so you have to go to CFD, right, to be able to model it properly. But we use some kind of we use some kind of penalizing condition. So we assume that circulation is not so good and it is going to heat up, so it will be penalizing for our analysis. But if you want to go further, we can go, of course. You can spend a life on those kind of analysis.
Please.
The code has the capabilities for even the future intentions to also use liquid metal as a tool.
For map?
Yes.
Yeah, I think they are now thinking of that, using map for like Gen 4 reactors.
Yes.
Yeah, so I'm going to, we are using map 5 at this time, and the next version should be 2-3 years, it should be map 6. And it's completely new, like it's the same equation, same physics, but with new IT, interface is different. And it should be able to model, like sodium cooled reactors, fast reactors, something like that. Yeah.
Please.
You talked about two transients that you model, SVO and LOCA. I was wondering if you did exactly the same runs, but considering the effect of implementing the emergency cooling condenser on top of it.
Yeah.
And also, I was wondering what happened to the hole that is on top of the reactor, whether how long can it last in case of LOCA or it's the ultimate heat sink.
Water wall, yes, it's a water wall. It's a big wall, right?
The ultimate sinking. You have the emergency cooling condenser, and that's linked to the wall that is serving as the thing. So
yeah.
do you have an estimation how long can it last?
Yeah, I have.
But yeah, one thing.
Yes, thank you. For the calculation in package 2, 5.2, we have calculation like we are not going to a severe accident because we have this safety condenser. So we model it. We model simply by equations what is the heat transfer depending on the temperature in the inlet and the outlet and the the gravity. When you have a natural circulation, the core is like a pump. The core, because of the density difference, like delta P, there is the delta P. Delta P is delta rho, the density J, G, H, gravity, H height of the core. You can calculate that by hand, and then do what will be the flow. You can estimate what is the flow, and then this flow going to the condenser, and you see what I mean? If you can do like hand calculation to estimate what could be the decay heat evacuated. So if you do the calculation through with a safety condenser, you have no core degradation at least for 7 days, because the time the water wall is heating up by itself. If you are not cooling it, of course there is no miracle, right? It's going to evaporate at a given time. You go to saturation, 100 degrees, and then you have it's less efficient. And if you have, let's say, no safety condenser, right? You go to severe accident, let's say after 24 hours, because you have like this battery life of 12 hours. So you have another 12 hours, living like there is no safety system, and then you go to severe accident, and then the water wall life, I would say, is like 10 days before it reaches like high temperatures. So if you do nothing after 10 days, we have troubles.
Please.
Well, since you discussed about the risk in the beginning, I have a question. What about the human error impact in the risk? Is there any analysis regarding this?
The human error impact in the wall safety strategy, right? You mentioned.
Yeah, in the safety analysis.
Safety analysis.
Yeah, for DBA it has big impact, So we were for DBA, let's say transient without co-degradation. So if the operator makes let's say mistake or takes more time than necessary to do an action, it could have an impact on the core degradation. It could degrade the core, and the core degradation was not expected, right? So yeah, but for severe accident, there is like you are going to the severe accident. The only different thing is the timing. When should we go to the severe accident? But it has an impact, because if you go, it's always better to go to a severe accident after a long time. Do you know why? Why? If you prefer to have a severe accident, is it right now or in 10 days?
In 10 days.
Why?
To rethink about rethink and try to solve the problem.
Yeah, it's a possibility, but I was thinking of a different thing. It's because of the decay heat, right? If you are going to have the severe accident right now, the decay heat is high. So you have to evacuate a lot of energy, right? If you have 10 days after, it's like in 10 days the decay heat is lower, and you can manage it more easily. So, yeah. But you're right. You know, human reliability is something looked very precisely within EDF. People are looking at that and making a lot of calculation. You know, let's say what is the probability there is a failure or things like that. And they use map for some calculation too. And they couple that to other code like I don't know, sorry, but I think it's Raven code like they're coupling things and make a different. You know, because the let's say the DBA analysis, it's very like a square. It's very strict, right? And maybe we can improve that. Or instead of, let's say, we let the operator 30 minutes to do something, maybe he has more. He has like 50 minutes. But if you do calculation, you can prove it. Otherwise, you have like key times, and you have to respect that, and sometimes it's penalizing, and you don't need that. Or I don't know if I'm explaining well, but it's a great part of a EDF job to look at.
Okay, Jen, one last question, since I don't see any other hand raised from the floor. One question about the coolability of the reactor pressure vessel and the corium inside by the pool that is inside the containment. What about testing or demonstration or experimental activities? Because the only example that I remember is about AP600. They declared the investor core-retention strategy. Mm-hmm. So they had some experimental testing with a sector, a very sort of slice, putting electrical heating and checking that the water is not going to critical flux, so to have a thermal crisis. So what about, can we rely, let's say, on the AP600 experiments, or, and this is a question also for Sean about the safety authority, should we need new experiments in order to demonstrate that?
It's a very good question, because we are talking a lot, for the new Earth project, which is close to the ESMR. So we are doing calculation at this time. We are using Ulpu correlation. You see that? There's like correlation for the heat flux based on experiment, right? It was a little bit like in the beginning of the 20,000 years, at that time. So we're using it, but it's only for steady state. But when you are going to have this kind of natural circulation, you have to prove it's going to establish. You will have natural circulation, and you will be able to extract the decay heat, right, through natural circulation. So we're thinking of making new, experiments for the exact design of the UR or ESMR, and in order to evaluate new correlation directly applicable. And also we expect to maybe couple codes. You see what I mean? Couple like map and maybe Gothic, American too, like improve CFD, like a kata code, but like 3D kata code, something in order to be able to estimate this natural circulation. But you're correct, we may need some new experiments, and the EDF is, working on that.
Sean, did NewScale put some emphasis or some issues like, because I suppose that also for NewScale, they are claiming investor core-retention, right?
Yeah, they do claim, I don't know that far enough to review.
Okay. Okay. One last question, please.
I just want to say that in the European project assessment now, it's one to have a look on the existing experimental data and how we can use it for SMRs.
Okay. Nice. Very good. Okay, that's all. Thank you, Sean. Thank you, Jeremy. Now we have time for the coffee break, and we will come back here. Remember that tomorrow you have to present 2 slides of the result of your working group. Whatever the result is, that's okay. Just to discuss. Thank you.